have taken very, not many lectures, 27 only so far. All right, so we have almost completed bending and shear stresses in beam. Now these shear stresses are also called transverse shear stresses. And the reason why it is called, the correct phrase should be transverse shear stress, because there is a longitudinal axis X and transverse to that is Z. So these shear stresses are acting on a plane perpendicular to X, along X, that means normal, whose normal is in X direction. So this is, I will draw only the section. So first the title of the today's, because they always ask. So bending and shear stresses continued. So you have a beam whose longitudinal section looks like, we have cut, this is X-axis. These directions are very important. So we are talking of this plane. That means if I look from this side, if I look from, standing on this side, then the cross section will look something like this. Let us take a rectangular cross section for simplicity. So it is going to look like this, and this is your y-axis and this is your z-axis. So these are shear bending stresses. Bending stresses means the bending stress is acting in X direction. See, when you have a bending and shear force acting on the cross section, so there will be bending stresses which will be like this, small, and then this will become compression, and this is why you have a variation that is triangular bending stress. So over here on this cross section of bending stresses, the direction of bending stresses are perpendicular to this plane. In which direction? X direction. Obviously it is acting in X direction. So the normal to the plane is X. So it is in X direction and it is linearly varying. Then in addition to that, you are also, now I cannot draw on the same because it will become very dirty. So let me have the vertical, supposing this is the same cross section. So shear stresses. In addition to this, you also have shear stresses which are acting on this surface. This is the surface X, vertical shear, and they are acting like this. 0, smaller. If you see in section, so shear stresses will be acting in the plane, a bigger arrow, because I think the other day we saw that what is the maximum shear stress, where does it occur? Neutral axis. So this will be the maximum arrow, and then as you go up, it will be smaller, and at this point it becomes 0. At the top surface it has to become 0 because the free surface tau zx is 0. Similarly, as you come down, it will be a smaller arrow. And what is the rate of variation? Trend of variation through depth. So this is the shear stresses. So this one is sigma x, and this one is tau x z. Here what is the stress that is acting? If it has to act shear here on the top surface, that will be tau zx. On the top surface, I am saying on the top surface of the beam, tau zx. Now this is 0 because it is a free surface. This top is free of stresses. So this is a free surface. And therefore this value should tau zx equal to tau xz. So therefore at here it must be 0, and the variation of this through depth, if this is the depth, of course it is not to the same scale, scale is different here, so this is the depth and this is x-axis, so variation is parabolic, that we have seen last time, that this varies parabolically, symmetrical parabola like this. So this is the magnitude of these shear stresses, they vary parabolically. Okay, now what is the value at the maximum value of shear stress? This, that means this ordinate from here to here, what is this value? Quickly tell me, what is shear stress, tau xz? We have done it last time, at z equal to 0. What is the value? It is VQ by IB. Everything is constant. V is constant, I is constant, B is constant, H is here, and Q, how do you define Q? If you want shear stress here, so it is the first moment of the area above that first moment of the area. So first moment of the area will be how much? What is Q here? First moment of the area, moment of this area above this line. So this area is B into, see, understand, directly you can find out the value of this shear stress which is acting at the neutral axis by taking the first moment of the area of half of this, because that is lying above that line. Okay, so first moment means area of this B into H by 2 is the area multiplied by first moment of the area multiplied by distance up to centroid H by 4. So Q, value of Q is this much. This is the Q at the neutral axis. Value of Q at the neutral axis. This is Q at Z equal to 0. Is anybody has got a doubt? See, if you don't understand these things, there is no point in going forward. Q is first moment of the area, Q. First moment of the area above that line. We have taken earlier Z. Z is varying from 0 to H by 2. So first moment of the area above Z line, horizontal line. So supposing I want to find out what is the magnitude, what is this magnitude. So I will take first moment of the area, V the shear force, so this is tau xz variation. So this one, I think last time also I gave you the variation as a function of Z. As a function of Z which gave us this variation. But only thing I did not find out this value exactly. I think I did find out. How much? Anyway, please tell me what is the value of Q. Now this is V, I equal to BHQ by 12 into B, centroid of this area, what is this distance? H by 4. First moment of the area means how do you find out center of gravity? So centroid of the area, so that is H by 4. So area multiplied by the distance to the centroid. So this is H by 4. So this is BH square by 8. So there is a BH. Now you please cut by 8. So B and B goes H square. This H square and HQ will go. Then what? This 12 will go on the, so 12 by 8. V divided by BH. What I am saying, you can find out the value of shear stress at any level. Last time we got a shear stress expression as a function of Z, and that is how we plotted this quadratic. It varies quadratically through the depth. Now V by, just is it okay? B by H, I have not checked. So charge 2 and 3. So it is 3 by 2. V the shear force acting on the, what is V? V is the total shear force acting on the section. There is also a moment that is acting. You cannot show everything on the same section. It will become very clumsy, but that is what you should understand. On this section, so V divided by BH into 3 by 2. Now, please tell me, supposing I did not know the variation of shear stress, the way we have found out yesterday, last time, and I would have asked, okay, this is the area, this is the area, this is the cross-sectional area, this is x-axis, this total sheet of paper is the area B, this is B, this is H, so, and this is shear force is acting like this. Please find out the shear stress. Anybody would say, okay, force is there, area is there, so I will divide the force by area. Average shear stress. So average shear stress acting on the, therefore, I will just take, this is 27 to 10. Okay, so average, please do not talk, average shear stress acting on the cross section, how much? It will be V, the total shear force, divided by the area. Divided by area is V into H. So this is average. Let us call this as tau average. Tau average. It does not take into account the variation of shear stresses through the depth. It gives you a rough value. Okay, average shear stress on the area is like this. So therefore, I can say that the shear stress tau maximum. Maximum means that is acting at z equal to 0. Tau maximum in the is equal to 3 by 2 into tau average. You see the so 1.5 times 1.5 times tau average. So we got a simple relation. Yes, if you take variation of shear, actually shear stress does not vary, it does not remain constant over the cross section. It varies parabolically through the depth. Width wise it will remain the same. B, in the B direction there is no variation, constant. Only through depth H it is varying. So average 1.5 times. So maximum shear stress is this. So this is for the, remember this is for the this is for the rectangular cross section. Now please find out this B into H. Yes, and we have found out, yes, the maximum shear stress is here. Of course it is. I hope you understand this. This is shear stress is always in the plane, not normal to the plane. So this is the shear stress distribution, and this value is more, so it is 1.5 times the average. Please do this same exercise for a circular cross section. Because the only thing that will change of the beam is the cross section. So do it for a circular solid. This is your Z. What else? Which other cross section? What will be? It will be 2 times. I don't know. You have to find out. So do this same exercise for this. Take a fiber at a distance Z of thickness dz, and then do this the way I have told you. and then find out the maximum shear stress at the neutral axis, and then find out the average shear stress. Average shear stress will be V divided by the area of the cross section. Area of the cross section equal to pi a square, and then you find out what is this maximum value which is acting on the neutral axis, and also find out what is the variation of the shear stress for circular cross section. It may not remain quadratic. Quadratic came only for rectangular cross section. So this one you please do the exercise for circular cross section. The other one is a triangular cross section. Triangle both. See, triangle center of gravity is here at 1/3 depth. This is Y. You can also have a triangle this way. The beam can also have center of gravity. So this is your Y and this is your Z. This is centroid. So triangular cross section, please do this. And last time I also gave you about I section and T section. I have given you the variation, the trend of the variation. Please find out exact values. So unless you do it yourself, you will not get confidence. It cannot be done in the in the examination. If you handle this only in the examination, then you will not be able to do it. You will make mistake. Please practice it, and then only you can become perfect. Okay, so this I will say shear stress is vertical shear. See, I don't want to complicate at the moment. I am leaving some portion right now because that will confuse you. We will take it up later on the shear stress, which is given in the book. See, we are not doing bending of cross sections which do not have a vertical plane of symmetry. We are doing only for bending which have a vertical plane of symmetry. That means Z axis divides the area of cross section into two halves, mirror image. If it is not so, if the cross section is not so, like a channel, C section, C section. Anyway, let me tell, since I have started, so let me, if the vertical, this one is, that means has no symmetry about vertical plane of, if the cross section, that means if the cross section has no vertical plane of symmetry, I will not complete this plane of symmetry. I will only mention this. That means we are talking of sections like this. Supposing, because this one is used, have you done trusses, design of truss? At least analysis you must have done, simple trusses. And if you see above yourself, whenever you see any truss, they use lot of these sections as purlins. Purlins means longitudinal members on the inclined. Truss will have some inclined members, main, and then there will be some members which will be running parallel to the axis along the length of the. They will be using this. This is called channel section or C section. Channel or C. Now this does not have, if it is going to be like this, if you are going to load it from top, this is a cross section. Length is there. This has a length. These are all rolled sections. These are all manufactured in factory, steel plants. So then this has your, what is this axis? Y axis. Now I cannot put my Z. there is no Z which will divide this section into two parts, two vertical, two mirror, there is no vertical plane of symmetry. So here what happens, if you apply a load from the top, this section will twist. This will twist. See, so far we were applying the load in the plane of the symmetry. So there was no question of twisting of the member. It was pure bending or bending with shear. Now here if you apply the load, if this is the length of the member, along the length, this looks like this, and the cross section was like this. And if it is loaded somewhere here, anywhere, if it is loaded, this will, in addition to bending, it will also, so this section will become something like this. After loads are applied, this section will twist. Yes, physically you can see that because it has no plane of symmetry. So if you apply a load in any point, it will going to twist. Now bending and twisting combined. Then also there is a shear, everything, three things. So we try to, there is a point about which if you apply a load here for this section, there is a point through which if the load is applied, then this twisting can be avoided. And for this section, there is a point here on this y-axis here, at some distance from the vertical web. This is web, by the way, this is called web, and this is called what? Flange. Flange. So there is this distance, y bar. If I apply a shear force, a vertical force here, P, through this, supposing I apply, that means I weld to this member some small strut and then apply the load here, then you will find that this section will not twist, it will have only, it will bend only, then it will be bending like in this section only. Then it will be like this, no bending, no twisting. No twisting. I am giving you only physical explanation. No twisting if P is applied. As shown. I am not giving you any theory. I am only explaining this, and this is very easy to understand. Yes, there is a point on y-axis about which if you can apply the load, then twisting can be avoided. Such a point is called shear center. So locate the point through which my load should be applied such that there is no twisting of the cross section. So this point is called shear center. S-H-E-A-R, shear, C-E-N-T-R. So concept of shear, we are only giving you here concept of not. And for this, I will have to find out not only vertical shear, I will just tell you this variation. This is the vertical shear, tau xz. See, once this member is thin, try to understand this. This is okay, there is no problem in understanding this vertical shear. If you apply a load is nothing but a shear, it will give some shear there at the cross section, and then there will be shear stress distribution, shear stress distribution vertical. Then in this member, this flange of course there will also be vertical shear xz, vertical. But then the variation, because the depth is so small, it will have more or less the same value throughout. But there is one more shear that is acting on this, and that is, if I take this, what is this shear? This direction. On the same plane, it is x plane. What is this direction? XY, yes. So on this there is also XY. This is XZ. We have been talking about XZ so far, vertical. Now there is also a horizontal shear component that should act on this. Now when you go up, so this one is again tau xy. So this shear, if you take, and shear, I think we have also defined a shear stress distribution will be tau xy will be varying like this from here to here, from here to here. So what happens, this shear and this shear, they must be equal and opposite. If you integrate this, variation of this will give you a force in this direction. This top one will give you a force in this direction. So actually, in a channel, you will have a force here, some H in this direction. You will have a force here H in this direction, and because of the vertical shear, this must be equal to your applied load shear, applied shear force at the cross section. If you integrate all these vertical shears, that must give me the vertical shear force. There is no, yes, vertical shear force acting at the cross section must be integral of these stresses, vertical shear stress. So this is V, this is H, this is H, and this and H is forming a couple like this. So it will try to twist the section in this direction. This will try to twist the section in this direction. So in order to counterbalance this, if you apply a load here, that will oppose the twisting, and therefore this is the point through which we must apply a vertical load so that my section does not get twisted. So that is the idea. That is the main idea about shear center. It is very easy, it is magnitude of tau xy, tau xy or tau xz, xy, yes. How will you find out xy? Yes, if there is a shear stress here, variation, shear stress variation, so shear stress is this shear stress Q. We have to find out Q for this. The Q will be first moment of this area at any. So I will find out what is the first moment of this about this axis. So I will take this entire area into multiplied by centroid distance, and that will give me the variation of shear stress. And at any cross section here, I have to cut this because I have to see the variation, because this will not remain constant. It will be varying from here to here. So I take a small section like this and find out here the shear stress tau xy is on this is small, there is a small, this is a cut. So what is the shear stress tau xy here? Tau xy here. So tau xy will be area of this multiplied by distance to the, from the centroid. So that way you can find out the Q. And then find out the value of this. So it is possible, and as this area will go on in next, supposing you want to find out here, so I will have to consider a bigger. So it will actually vary linearly. because here this only the length is increasing, only one dimension is increasing. So this shear stress will vary. In fact, this shear stress, I can draw it on the next. This is 2, this is 3, 27. Yes. So this is the cross section. And this cross section is subjected to a vertical shear. Let us set any. Shear center. So centroid may be somewhere here. Of this cross section, this could be centroid G. That is different. So there is difference between centroid and shear center. This is shear center. So this is now I want to draw the variation. Center line. Then see, this shear stress will vary linearly on this. This is varying linearly. Similarly, here also it will vary linearly, because only this one is changing. Sorry, it's going up the. And in this one, when you come to the here, this shear and this vertical shear, they must be equal. See, this shear and the vertical shear must be equal, and then it will vary like this. So please do 1 or 2 exercises, but we wanted to, we are not doing in greater detail shear center, but yes, I have given you the concept, what is shear center and how shear center can be found out. And you apply the force to a point such that this this moment is counterbalanced. Moment is counterbalanced. So that is all. So you can find out. Okay. Now next is now we'll do something quickly, which is a very simple. Supposing sometimes you have to, so far we have been finding out stress variations, and right from the beginning I am saying that we are doing linear elastic analysis. Linear elastic analysis means once is displacements are small. First assumption for a linear elastic analysis is displacements are small. Now what is that small?